Recent records from observatories around the world have revealed something completely unexpected. 9 distinct formations have been detected orbiting in the vicinity of 3I/Atlas, the interstellar visitor that has already intrigued astronomers since its arrival in the solar system. The captured images show these objects maintaining a configuration that defies conventional astrophysics expectations. The observed pattern immediately caught the attention of specialized teams across multiple continents, who redirected their instruments to monitor this phenomenon in real time. What makes this discovery truly exceptional is the extreme rarity of this type of cosmic grouping. In decades of celestial body observation, nothing similar had been documented with such clarity, especially involving an object of interstellar origin. The preliminary analysis of the behavior of these 9 companions brought even more questions than answers. The movements appear to exhibit a synchronization that strongly suggests a common origin, as if all were born from the same cataclysmic event or fragmentation process. The brightness variations recorded throughout the observations indicate that each fragment possesses slightly different composition from the others, presenting unique spectral signatures that defy simple classifications. Even more intriguing is the fact that certain aspects of this cosmic dance remain completely inexplicable by current models. The relative velocity between the objects, the apparent stability of their trajectories, and the absence of expected gravitational dispersion create a puzzle that is mobilizing the planet's leading research centers in orbital dynamics. What makes this grouping even more fascinating is the way the fragments seem to respond to gravitational influences from the surrounding environment. Computer simulations executed by several independent teams show that the observed configuration should not remain stable for more than a few days or weeks, considering the forces at play. However, data collected over consecutive weeks demonstrate surprising persistence of this formation, as if some not yet understood mechanism were maintaining the objects in their relative positions. This contradiction between theory and observation is forcing scientists to reconsider fundamental assumptions about how small celestial bodies interact in complex gravitational environments, especially when involving objects of interstellar origin that may carry physical properties completely different from those found in bodies native to the solar system. The spatial distribution of the 9 fragments presents additional peculiarities that deepen the mystery surrounding this discovery. Rather than forming a simple linear pattern or random scatter, the objects appear arranged in what some researchers describe as a 3-dimensional helical configuration, spiraling outward from the central body in a manner that suggests organized structure rather than chaotic dispersion. This geometric arrangement has no precedent in documented astronomical observations and challenges existing theories about how fragmenting bodies behave in space. Some scientists have even speculated that this pattern might indicate the fragments are still connected by some form of tenuous material, perhaps extremely thin filaments of dust or gas that remain invisible to current detection methods but exert subtle influences on the fragments' trajectories. If confirmed, such a discovery would revolutionize our understanding of how celestial bodies fragment and interact across vast cosmic distances. Diametrically opposed interpretations have emerged within the scientific community regarding the timeline of this fragmentation event. One camp argues that the observed configuration is extremely fresh, perhaps occurring within the last few weeks or even days, which would make researchers extraordinarily fortunate to witness such a rare cosmic event in progress. This interpretation is supported by the apparent cohesion of the group and the minimal dispersion observed so far. The opposing view suggests that these fragments may have been traveling together for far longer, possibly since before 3I/Atlas entered the solar system, and only became detectable now due to changes in lighting conditions, viewing angles, or increased observational sensitivity. This latter interpretation carries profound implications, suggesting that interstellar objects might commonly travel in groups or clusters that remain undetected until specific observational conditions are met, fundamentally altering our census and understanding of interstellar visitor populations. Faced with this enigma, 3 main hypotheses have emerged in scientific circles to explain the emergence of these mysterious objects. The first theory proposes that we are witnessing the results of a recent fragmentation of 3I/Atlas itself, possibly caused by thermal stress when approaching the Sun or by gravitational tidal forces that ruptured its internal structure. The second possibility raises the idea that these fragments are actually remnants captured during the main object's long interstellar journey, cosmic material that was trapped by 3I/Atlas's gravity at some point in its trajectory through deep space. The third hypothesis, perhaps the most controversial, suggests a possible interaction with dust clouds and debris present in the solar system itself, which could have created temporary condensations or revealed previously invisible material that had been traveling alongside the interstellar visitor from the beginning. Each of these theories carries profound implications for our understanding of cosmic processes. If fragmentation is confirmed as the primary cause, this would mean that 3I/Atlas possesses an internal structure much more fragile or complex than initially estimated, possibly indicating a porous or stratified composition that reacts dramatically to temperature and pressure changes encountered in its passage through the solar system. On the other hand, if the fragments are material captured on its interstellar journey, we would be facing a unique opportunity to study matter originating from completely different regions of the galaxy, potentially offering clues about the physical and chemical conditions prevailing in other stellar systems. The third possibility, involving interaction with local material, would open fascinating questions about how interstellar objects can temporarily accumulate or disturb matter encountered in their path, creating transient phenomena that challenge our tracking and analysis capabilities. Testing these competing hypotheses requires sophisticated observational strategies that push current technology to its limits. Researchers are employing a multi-wavelength approach, observing the fragments simultaneously in visible light, infrared, and even attempting radio observations to detect any subtle emissions that might reveal their composition or activity level. Polarimetry measurements are being conducted to understand the surface properties and particle size distribution in any potential dust clouds surrounding the fragments. High-resolution spectroscopy is being used to search for absorption or emission lines that could fingerprint specific chemical compounds and help determine whether the fragments share identical composition with the main body or represent foreign material. The coordination required for these observations is unprecedented, with observatories across different time zones working in relay to maintain continuous monitoring as the grouping moves through space, ensuring no critical changes or events go unrecorded. The international scientific community finds itself genuinely intrigued by this unprecedented phenomenon. The observed formation resembles what some researchers are informally calling mini-swarms, structures that had never been detected in similar contexts and that have no clear analogues in existing astronomical literature. One of the main difficulties faced by research teams is determining precisely the individual mass of each fragment and evaluating the long-term orbital stability of this grouping. The data collected so far prove incompatible with traditional models describing the dynamics of multi-body systems, suggesting that additional factors not yet identified are at play. This incompatibility is not merely an academic curiosity. It points to fundamental gaps in our understanding of how interstellar objects behave when traversing complex gravitational environments. The implications of this discovery for understanding the true origin and nature of 3I/Atlas are profound and potentially revolutionary. The grouping of fragments can function as a unique window into the internal structure of the main object, revealing layers and compositions that would remain hidden in conventional observations of its surface. There is growing evidence that 3I/Atlas has undergone extreme events in its cosmic history, possibly violent collisions or close encounters with stars that shaped its current configuration in ways we are only beginning to comprehend. Comparisons with other known interstellar visitors, such as Oumuamua and Comet 2I/Borisov, show that 3I/Atlas presents unique characteristics that do not fit the patterns established by these predecessors, suggesting a much greater diversity of interstellar objects than previously imagined. Spectroscopic analysis of the fragments is revealing peculiarities that amplify the mystery rather than clarifying it. Some of the objects present signatures suggesting the presence of volatile organic compounds, while others appear to exhibit characteristics more compatible with rocky or metallic materials. This heterogeneity in chemical composition within an apparently related group is extremely uncommon and raises questions about the formation and evolution processes of the main body. Additionally, detailed photometric measurements indicate that at least 3 of the 9 fragments demonstrate periodic brightness variations that cannot be easily explained by simple rotation alone, suggesting complex irregular shapes or possibly even residual surface activity, such as ice sublimation or dust particle release. These details add layers of complexity to an already quite intricate puzzle. Beyond the immediate scientific questions, this discovery has sparked broader philosophical discussions about the nature of interstellar space and what other surprises might await detection. The existence of complex, multi-object systems traveling between stars challenges the simplified models that have dominated thinking about interstellar visitors for decades. It raises the possibility that interstellar space is far more populated and dynamic than current detection capabilities reveal, with countless small objects, debris fields, and fragmentary systems passing through our solar system undetected. This realization has prompted calls for enhanced sky survey programs specifically designed to detect faint, fast-moving objects that might be part of similar groupings. The technological and financial investments required for such programs are substantial, but the potential scientific return, a complete census of interstellar visitors and their associated companions, could fundamentally transform our understanding of galactic dynamics and the exchange of material between stellar systems. The discovery has also reignited discussions about planetary defense and the potential hazards posed by unexpected visitors from interstellar space. While 3I/Atlas and its companions pose no threat to Earth on their current trajectory, the revelation that interstellar objects can arrive accompanied by multiple fragments raises new considerations for impact risk assessment. If a hazardous interstellar object were detected on a collision course with Earth, would it too be accompanied by a swarm of smaller fragments that would need to be tracked and potentially deflected independently? These questions are prompting space agencies to review and update their near-Earth object monitoring protocols to account for the possibility of multi-body interstellar threats. The coordination between astronomical research and planetary defense initiatives is becoming increasingly sophisticated as a direct result of the mysteries presented by 3I/Atlas and its enigmatic companions. The near future promises significant advances in understanding this cosmic mystery. State-of-the-art telescopes in operation around the globe are being programmed to measure with greater precision both the exact distance of each fragment relative to the main body and the detailed chemical composition of their surfaces. There is also the real possibility that more fragments will appear as observations become more refined and instruments with different capabilities turn toward this region of space. The upcoming observation windows, especially those scheduled for when 3I/Atlas reaches specific points in its orbit, will be crucial for resolving some of the most pressing questions. For those following the mysteries of the cosmos, this is a unique moment. Following the scientific reports that will be published in the coming weeks and months may reveal discoveries that rewrite our understanding not only of interstellar objects, but of the very evolution and dynamics of the universe around us. Tentar novamentio Claude pod cometer eros. Confira semper as respostas.